want to set up some sort of process where you do some serial processing on the GPU, pass the data off over this bus, stick it in video DRAM, let the GPU compute on it for a while, and then pass it back over here, and eventually it reaches the CPU again. Your goal, if you're trying to compute smart, is to set up everything early on so the GPU has all the resources it needs, and you never have to send it over the bus again. So one of the goals of fast computing is to keep everything as local as you possibly can. And when you actually set up GPU workloads, you want to have it go out to main video memory as little as possible. You want to stick in your cache and local references as much as possible. We'll talk more about it later, but basically this is one of the keys to speed, is realizing that the farther away you step data-wise, the slower you're going to get. And I can't tell you how much acrobatics goes on internally in the hardware and the driver in order to make sure that that works efficiently. Yeah?
Was there ever an attempt to marry the CPU and GPU more directly?
Yeah, absolutely. So a couple of years ago, AMD bought ATI, and that was what all anybody could talk about at the time, was GPU and CPU on the same chip. And the idea is that, well, gee, you know, if we can basically short circuit everything and stick this bus right here, how cool would that be? Well, yeah, so, I mean, we're already talking about, I think, Fermi, well, I don't even know if I can say, but we're talking about large die sizes for the GPU already. And the CPUs are large die sizes. So if you were to try and combine them on the same die, you get really large dies. And the problem with really large dies is that the silicon manufacturing process has defects. And the larger your die, the greater the chance you're going to have a defect in any given die, and the lower your yield, and the less money you're going to make. So your next step becomes, all right, fine, if I can't put it on the same chip, can I stick the chips together and have, you know, some super fast bus that basically makes them kind of the same chip? You can do that. You get heat issues and other things like that that you have to deal with. But you can do it. But there are so many difficulties in trying to get that really close packaging going. AMD is still working on that. They still think it's worthwhile, and it very well may be, but it's a hard problem, and as long as they've been working on it, they have not yet solved it in a way that's commercially marketable. I'm not saying that they won't be able to do it. Intel's certainly looking at it, and that's actually what Larrabee is, to a large extent. I don't know if you guys have heard Larrabee, but Larrabee is Intel's answer to a lot of this, which is basically, you know, you guys have seen Intel Xeon chips go from, like, you know, 2 cores to 4 cores, and I think they're talking about 8, 16-core chips. And, you know, you hear about these really huge core chips that they're talking about. Well, Larrabee is a whole bunch of cores that are good at being a CPU and at being a GPU and combined together with cache. And at any one time, the core could be used for GPU loads and then switch over later on to CPU loads. And so that's kind of how Intel is trying to deal with it. Not trying to say, this is a specialized GPU, this is a specialized CPU, and we're going to stick them together on the same die. Instead, we're going to stick a whole lot of cores that are good at both together on the same die, and we think that's going to be awesome. Now, all right, take it with a grain of salt. I work for NVIDIA, not Intel. So, you know, I have certain views on that. I may not be right. I'm going to tell you what I think. I think, honestly, that's a cool idea. I think it's a very hard idea. And I think Intel's finding that it's a very hard idea. Larrabee has been delayed. Larrabee 1.0 was essentially canceled. Larrabee 2.0 is based on Larrabee 1.0, and they haven't said it's canceled yet, but it sounds like it's going to be canceled. Larrabee 3.0 is a big reworking of the whole thing, and it sounds, from what I can understand, and this isn't like internal NVIDIA sources, this is just net rumoring. From what I can understand, Larrabee 3.0 is really where they're pinning their hopes, saying, well, we got a lot of things wrong last time, but we think we have it right now. So that may be the future of things. And if it is, I wish them the best of luck. You know, obviously, we think we've got something pretty cool going on that can answer that, but a lot of smart people have decided that that's the way to do things. So, yeah, anyway, does that answer your question? All right. So anyway, I'll kind of whiteboard about this more later, but this is the main carry-away point that I want you guys to take, is that memory locality is huge. Anytime you're programming parallel, well, probably anything, but parallel especially, You want to take advantage of memory locality so that you don't completely bottleneck everything on your memory architecture. So there's a bunch of different kinds of locality that we deal with regularly. So sysmem versus vidmem, that's the biggest top level thing. Certain things, if you're going to be streaming the data always across the bus anyway, there's certain things that it never makes sense to cache in video RAM. So if you have some sort of texture data or vertex data or index data or something like that the application is going to change on every single frame, it doesn't make sense to stick it in video RAM. But as time changes, there's fewer and fewer of those loads. Game programmers are getting better and better at sticking things in video RAM and just dynamically creating new content based off what's stored in video RAM with a little bit of command sent down to the GPU. By adding the geometry shader and tessellation shader, working with PhysX, working with OpenCL, Direct Compute, CUDA, all of those things, you're able to create a lot more dynamic stuff on the GPU that you can just keep feeding back without having to go across that bus. But that's an important distinction, is knowing when to put things where. Next thing is spatial locality. When you're writing shaders, and also when you're working on compute stuff, you don't want to be grabbing stuff from all over the place. If you can help it, you want to grab resources that are all next to each other. So, if you're working on, say, a pixel shader, you don't want to be grabbing things from 15 different textures and random spots all over your textures, because then you can't use your cache well, and you may even wind up with cases where you run out of video memory if you do that, and you're going to go across the bus with your shader, and that's a pit you don't want to fall into. Lastly, temporal locality. If one particular shader run is grabbing things that are all local, but the next shader run is grabbing things that are all over the place, that's very far apart spatially, that's a temporal problem, because as you step forward in time, you're kind of gathering scattered all over the place. And so if you can program things in a way that makes each step grab just a little bit further, and stay close together in time and space, that's a win. And we have all sorts of weird texture layout schemes on the GPU that try and help you with these. I don't know if you guys have heard of space filling curves, Hilbert curves, things like that, but it's basically a graphical way of laying memory out that looks kind of random and scattered, that guarantees that when you're accessing things, it's all pretty close together. And I can go into detail later if people are interested, but for now I'm going to kind of just push on. So the big take home, by the way, and I won't name names, but one of the biggest things we see, whether it's graphics or compute or whatever, is people who change their memory resources a lot, allocate a lot of textures, free them up, allocate tons of textures, free them up, things like that, get terrible perf. The people who set it up once and just run from there get really great perf. And really smart people who really know their areas very well make this mistake all the time. Game programmers tend not to, but sometimes they do. People making professional apps, video processing stuff, that really know their domain very well, but don't necessarily know the CPU and GPU as well, those are the people who make this sort of mistake all the time. So it's important to have in the back of your mind that, how this hardware works and what the problems are when you're writing this stuff. And so I've really been harping on, I just want to toss it one last time, computation and memory. Don't forget either, because if you do, you're going to suffer. All right, so Fermi is the next thing coming out. I'll say it first off, yeah, we're late. Everybody knows we're late. But it should be out soon. And it's pretty public record now how things are laid out, so I can talk a little bit about it. This is the basic chip layout, kind of in a simplified